So today what we're going to do is we're going to talk about graphing rational functions, okay? It's not going to be anything too deep. It's just going to be an example, and we're going to graph this rational function, and I'm going to teach you how to graph it. So, graphing rational functions. And now I'm going to go ahead and give you the problem here. Give me 1 second. Let me adjust that. Okay, so let's say that we have f of x is equal to x squared plus x minus 2 over x squared plus 2x minus 3. Okay, what we need to do is we want to graph this. That's the main goal, is for us to graph this. But we need a couple of logistics first before we can do that. What we need to do, let's go ahead and make that sign over here. What we need to do. Okay, let's see. The first thing, we need to find the, let's call it the domain restrictions. The domain restrictions, or we can call them our holes. That's the first thing that we would need to find. The second thing that we need to find would be our zeros. And this will be helpful to you later, and I'll show you how. Then the third thing we should find would be our horizontal and our vertical asymptotes. Lastly, we're going to graph by the calculator, and we're going to graph by hand. And we're going to compare these two, and I'll show you exactly how exactly they are the same. Okay, so with this function here, the first thing we need to do is domain restrictions. Now, the way we get a domain restriction is we need to first factor this. So that's the first thing we'll do. We'll factor this. So we'd get y is equal to x plus 2 times x minus 1 when we factor that numerator, and factoring the denominator here, we'll get x, we'll get x plus 3 times x minus 1. That'll give us minus 3, then add, okay, plus it. Good. Now, in order to find the domain restrictions, I'm going to teach you a shortcut here. The shortcut says that the domain restrictions, or the holes in my graph, are only what's common between the numerator and the denominator. Though that's my holes. That's my holes in the graph, is what's common. So all we do is take what's common in the numerator and the denominator, we set it equal to 0, which will be what? X minus 1. We set that equal to 0, and we solve, we get x is equal to positive 1. Simple as that. That there is my domain restriction. Or, as we call it, if it's a domain restriction, that means there's no value of x there. So we call it a hole in our graph, or a discontinuity, meaning it stops it from being continuous. So a hole or discontinuity. Now next, what we want to do, let's go ahead and find these zeros here. So if you don't remember, I just wrote the note up here for you, but this is actually what this graph should look like, what this function is. F of x is equal to p of x over q of x. That's what this function actually says here. That's what it is. So when I put here p of x is equal to 0, what that meant is that that's how you find the zero. So p of x being the numerator, p of x, and then this is q of x, meaning we're going to set this numerator equal to 0. Well, this numerator is equal to that because it's just a factored form. So if we go ahead and set this numerator x plus 2 equal to 0, and then x minus, One second, I forgot to cancel these out here. We need to cancel those out. Right after we find the domain restriction and the commons, we're basically going to simplify this and we're going to cancel those out. So then we'll be left with y is equal to x plus 2 over x plus 3. Got a little bit ahead of myself there. So we're actually going to now find these zeros by setting this function equal to 0, this p of x function, which is this here, right? P of x. So we'll set that equal to 0. So we just take x plus 2 equals 0. We solve, we'll get x is equal to a negative 2. Simple as that. That is my 0. Okay? Moving on down, we'll find our horizontal asymptote and our vertical asymptotes. Now, if you recall, it says if they have the same degree, which these both are linear, they have the same degree of 1, then what we would have actually is a horizontal asymptote being the coefficients of our two functions. So let's go ahead and write that. Y is equal to, let me get a different color. Y is equal to the p of x leading coefficient over q of x leading coefficient. So that's what it actually be equal to. So we can substitute y is equal to, because both coefficients are 1, since it's nothing in front of that x but 1 basically, it'd be 1 over 1, which would be 1. And y is equal to 1. That is my horizontal asymptote. Simple as that. Now this only works when you put the coefficients of the p of x over q of x when your degrees are the same. But we have different rules for when your degrees are different. They can form an oblique asymptote when p of x is greater than q of x, or they can form an asymptote of 0 when the denominator q of x is actually greater than the numerator p of x. So from here we found our horizontal asymptote. Let's find our vertical asymptote. Now, if you think here for a second, a vertical asymptote, so a vertical asymptote means where my function is undefined. And we have different notations here. You can just say where your function's undefined, or where it's 0, or where it's infinity. Because if something being undefined is actually infinity, but we won't go into that right now. We'll talk about that later with limits. So this is the vertical asymptote. So what will make what will make my function 0? Well, the way we do that is we remember finding stuff that's how to find when a function's undefined. We do. So we take that, x plus 3, we set it equal to 0. We get x is equal to a negative 3. That x is equal to a negative 3, that is what I call my vertical asymptote. Okay? Moving on from here, after my vertical asymptotes, what we will then find would be our, let's go ahead and check off some stuff. We got the domain and range, we got our zeros, we got our horizontal and vertical asymptote. Now it's time to graph this bad boy here. Well, let's go ahead and do it. We have everything we need to graph. We have our 0 at x is equal to a negative 2. We have our vertical asymptote at x is equal to x is equal to a negative 3. Right there. We have our horizontal asymptote at y is equal to a 1. And what else would we? Oh, and we have our whole at x is equal to 1. Perfect. So this is everything that I need to graph this function here. Now let's go ahead and do it. I'm going to go ahead and draw the graph. And then we'll graph it on the graphing calculator and just see the comparison of the two that we get. We'll compare those two. Let me try to get a little bit bigger pen here. Okay, so let's go ahead and look at it here. Let me get out the color. Now, what we want to do first, let's go ahead and graph our asymptote, our vertical asymptote. That's the first thing we're going to do. Then our horizontal asymptote. Then we'll graph our zeros. Then we'll actually see if we can sketch the behavior of this graph here. So horizontal asymptote we have at x is equal to a -3. We'll say that's about right there. Then we have a vertical we have a horizontal asymptote. This is our vertical asymptote. Oops. This is our vertical asymptote. Our vertical asymptote at that point. But we also have our what? We need to go ahead and graph our other asymptote, which is our horizontal, which will be y is equal to 1, which will be about right there. Y is equal to 1. Now, this is not drawn to completely scale. This is just a random rough sketch of the graph. Now, 0, x is equal to -2. X is equal to -2. That'll be, if -3 is right here, -2 should be somewhere about right here. And that'll be that 0 there. And the last thing is the hole, which we can do later at the end. Now we're going to go ahead and just kind of sketch this graph. Now we know that it's going to hug this asymptote. So it's coming from this way, and it needs to cross through that point there, and probably stretch on out there. So it came through, crossed through this x-intercept here, and it went on this way to positive infinity. Okay, now we have up here as well, in between these. Well, it'll look just like this. Very simple. Goes straight up like that. Okay? Now, generally, since we're just doing a rough sketch of this graph, it's not important for us to really have points for it. Now some teachers, they will require you to actually have points, but I'm not going to actually show you what points, just because for the sake of time, and also we'll get basically the same looking graph because all of this information here allowed me to get it. Now, let's go ahead and show, basically this would be this graph. Let's go ahead and label this stuff here so you don't get confused. This is the vertical asymptote as labeled there. This is the horizontal asymptote. This is the 0, so that's where my function crosses the x-axis. And of course here we just have our rational wings, our rational graph actually. Oh, I forgot about something. We forgot about this hole down here. We have a hole at x is equal to 1 because that value is not defined there. So for x, so we need to go ahead and erase a little bit so we can get that hole to disappear. X equals 1 will be about right there. So we're going to erase that hole in there, and we'll fill it in with a regular old circle. We just fill it in with a circle. Okay, so that's basically how that graph would look with a hole there. And we're going to go ahead and graph it on this graphing calculator just so we can see how it is the same indeed. What we would put parentheses, we get an x squared plus x minus 2 plus x minus 2, and then we'll close that parentheses and divide by, again, let's go ahead and open up parentheses, x squared, open up parentheses, raised to the power of x squared plus 2x minus 3. So plus 2x minus 3. Plus 2x minus 3. Okay, and we're going to go ahead and close that off there and press graph, and we'll see our graph function exist. Now, it may not look like it's a hole here. It may not look like it's a hole here, but indeed it is a little jump hole there. It's not completely continuous, as we can see, but it's not really a good graph of it. But we know that it's a hole there by hand, so we obviously put it there. Now, if we look at this graph, we see that we have the function coming from this side, from negative infinity, going up to this vertical asymptote of x is equal to -3. It goes from negative infinity to -3, and we see that here. We see it comes from here, and it doesn't quite touch that vertical asymptote. It gets very close to it, as we can see. The same thing here. It comes from negative infinity. Out there, and it gets close as it approaches this -3. But it doesn't quite touch it because there's no value that's defined there. Same thing with here. Then we come down from here, and we're coming right along our horizontal and our vertical asymptote in between here, just like we have here. And of course, we have the hole in the graph right there. Of course, we have that hole, which basically the hole means that it's no value that's defined at that point particularly. Okay, so I've taught you a lot here, showed you a lot just in this one example problem. I'm going to go ahead and show you these steps. I'm going to go ahead and show you the steps of how to actually get these things, the formula for them basically. So the zero, let's look at that. The zero would be equal to p of x is equal to 0. So basically what this is saying, set the numerator equal to 0. And solve. And solve. That's all you're going to do. That's how you find the zeros. Now, the vertical asymptotes. Vertical asymptotes. All you're going to do here is q of x is equal to 0. So basically set the denominator equal to 0 and solve. Okay? Now, the horizontal asymptote, this one here, all we're going to do, they have this one has 3 rules here, but we'll go ahead and talk about each one of them. Put this in here. So if p of x is greater than q of x, then this equals what we call a slant or an oblique asymptote. Okay? Now, if we have p of x is less than, give me one second, this keeps growing here. Okay, if we have p of x is less than q of x, then we would have a what am I saying? Asymptote of 0. If p of x is less than q of x. So basically, if q of x is greater than p of x, we'd have a vertical asymptote with y is equal to 0. Y is equal to 0. Now, if we take, if we actually have them equal to each other, which we did in this problem, p of x is equal to q of x, we'd actually end up with the leading coefficient of p of x divided by leading coefficient of q of x. Okay? So these are the rules for the horizontal asymptotes, and this is the one I'll put a star by the one we actually used in this case, which was the one where they're equal. So we use the one where basically we would use the coefficients of our p of x and our q of x. Now just for the holes, that's the last thing we're going to do. So holes, how we find the holes? Basically the holes would be factor. This is how you find. You factor, then you find the common. You find the common factor in the numerator and denominator, then solve. Then you solve. That's all you do. Then you solve for that. And remember, then cancel out the commons. Cancel out the commons, okay? So basically, this is a set of rules here. You can go ahead and pause it, take a picture, whatever you need to do to get this down. But basically, this is the set of rules that we would use here to actually find each of these. And these are the different steps you would take. And generally, from these, we'd first graph. So we'd first graph the vertical asymptote, then we'd graph the horizontal asymptote, then we graph the zeros, then we graph the whole. No, let's go ahead and graph. Sorry, we graph the function we graph the function actually first. Then after the function, the fifth thing would be to insert any holes that you have. Okay, so this concludes our video on rational function and graphing. I'll do one more example in the next video, but really this is a pretty in-depth example here, where we talked about all the the entire process for graphing rational functions and understanding the logistics of what's actually going into play when you graph these rational functions. And as you can see, we confirmed our rational function from this graph here on my graphing calculator. We confirmed it with our same graph that we have here. Okay, that concludes this video.